So this is a joint work with Hernan Melgrati from the University of Buenos Aires. And since this is the first talk of the session on sessions, I thought about giving a one-slide introduction on sessions. So at least in this talk, a session is a private communication channel that connects to processes P and Q, and which can use this channel for exchanging messages. And what is interesting about these is that each endpoint of the session is associated with a type, a session type, which is a type level specification of the protocol that the two processes are supposed to comply with in order to interact successfully. So in this case, for example, the process P is supposed to send two integer numbers to Q and then to receive an integer number from Q. And Q, on the other hand, will behave in a dual way. So every output action on one side of the session is matched by corresponding input action on the other side, and vice versa. We can think of session types as finite state automata specifying a communication protocol. So what we want to do in this work is to pair session types with more precise specifications concerning the communication protocol between two processes. And in particular, we want to be able to reason about the content of the messages that are exchanged between the two processes. So for example here, if we take the session type bang int, question mark int, and we might want to be a little bit more precise. And for example, we might want to say that the second integer number that is sent in this session is supposed to be different from 0. And similarly, we might want to say that the integer number that we receive at the end of the communication in this case is supposed to be a strictly positive number. So contract systems that are capable of specifying these kind of properties have been studied for quite a long time. And in fact, these two papers that I've mentioned in this slide have been a major source of inspiration for our work. So in these two papers, contract systems are studied for higher order functions and mutable objects. And the reasons why these works are connected with our is that there are striking analogies between functions, mutable objects, and sessions. So just as you can have higher order functions, you can have higher order sessions. That is a session on which you communicate the endpoint of another session. Just as you might have a mutable object with operations put and get that you can use for inserting values into the object or retrieving or removing values from the object, then you have operations send and receive for sending messages on the session and receiving messages from the session. However, unlike conventional mutable objects, there are differences. In particular, the order in which we are supposed to perform these send and receive operations is not free, but is constrained by the session type. The type of the messages that we send and receive may change over time as the session progresses. And similarly, the properties of the messages that we exchange in the session may vary with time, again, as the session progresses. So there is this new element here, the fact that the contract of the session evolves and must be updated at runtime as the session goes on. So in order to study this setting, we work with a language which has these four components. There is a functional core, which is basically lambda calculus. We have threads for modeling parallel processes communicating with each other. A set of communication primitives for sending and receiving messages over sessions, and then a set of, I would say, rather standard constructs for monitoring expressions at runtime. And in particular, we have this expression over here, which is monitored by a contract C, and we have two labels, P and Q, that allow us to identify the modules in the program which are responsible for the values respectively flowing out of E and flowing into E. So these ingredients so far are quite standard. The novelty is that we add a set of constants for describing structured contracts over sessions. So for example, the contract send C, CD applied to two contracts CD is a contract that we can use to describe a session endpoint on which we are supposed to send a message that satisfies the contract C, and after this operation we are supposed to use the session according to the contract D. So let's see an example. So we take the session type that I've shown you before, and we try to write down a term which describes the contract listed here. So for the first communication, we don't have any constraint. So we use the NEC contract, which means here we are free to send any message. After that, we are supposed to send a number, which must be different from 0. And we specify that using a so-called flat contract. And in the end, we will receive a number which we expect to be greater than or equal to 0. So as you can see, we can use these constants to describe in a structured way the contract of the whole session. A typical program in this language looks like this. So here we have, first of all, we establish a connection with the server, and we obtain a session endpoint. And then we use this session endpoint for performing a sequence of input-output operations. In this case, we do 2 sends and 1 receive. And what I want to stress on this slide is the fact that if you look carefully, you will see that every time we use a session endpoint for performing an input-output operation, the operation in the end will return, in fact, the very same session endpoint, which we rebind with this sequence of LEDs, and we use for the rest of the session. So this rebinding, this sequence of rebindings is necessary because the type of A, the type of the session endpoint, will change as we use the endpoint, as I've shown here on the right, where you can see these type annotations concerning the endpoint A. And so the idea is that we can exploit the same mechanism for updating not just the type of the endpoint, but also the contract associated with it. So this is the idea, and now we will see how this actually happens. The difference is that the type of the endpoint is updated at compile time, whereas the contract of the endpoint will be updated at runtime as the session progresses. So let's take 2 processes that communicate with each other. They are connected through the session A. As you can see, the sender process is willing to send a message M to the receiver, and the endpoint it is using is monitored by a contract saying that we are supposed to use this endpoint for sending a message that satisfies the contract C, and after that we will use the rest of the session according to D. So at this stage we cannot perform the communication yet. First of all, we have to redistribute the monitors so that we check whether the message M does satisfy the contract C, and we flip, as usual in these contract systems, the labels P and Q that we had at the beginning to keep track of the correct responsibilities of the process. But we also wrap the whole application with a new monitor which refers to the contract D. At this point, let's suppose that the message M satisfies the contract C. So this means that eventually this monitor will disappear, and we end up in a configuration where the communication can happen. So now the message M migrates to the receiver side, where it is paired with the endpoint on the receiver side. And the whole application send MA reduces to the endpoint A, which is now wrapped with the contract D, which describes how we are supposed to use the session in the rest of the conversation. So you see that by means of this mechanism, we have updated the original contract of the endpoint from this form to this form. So this is the case of a first order output, where we send the message which is not another session endpoint. When we have a higher order output, initially the situation is similar in the sense that, again, we redistribute the monitors so that the message that we are sending, B in this case, is monitored by the contract C that it is supposed to satisfy. But now, B is just a name, is just a session endpoint, and there is no check that we can perform at this time to verify whether this endpoint does satisfy C or not. So in fact, this is a value, and this is what we actually transmit to the receiver side. So in this case, the monitor around B remains attached to B and is transmitted along with the message to the receiver side, and the monitor around A is updated as before. So this is basically the key mechanism that allows us to reason and to monitor sessions by updating their contract as the session goes on. Now, when one defines systems, monitoring systems like this, a very natural question is, well, if I write a correct module in a system, a module that does not violate any contracts of the session it uses, can it be that my module can be blamed anyway because of a contract violation? And answering this question is usually quite difficult, especially when we have higher order features. So here we have an example where we have three processes, P, Q, and R, which are connected by two sessions, A and B. And if you observe the contracts, you see that P will receive from Q a session endpoint on which P is allowed to send anything. On the other hand, the session connecting Q and R is such that R is expecting to receive a number that is strictly positive. So what happens here is that Q might decide to send B, the endpoint B, to P. At this point, P thinks that it is safe to send a negative number on this endpoint, whereas R expects a positive number. And by the time we realize that there is something wrong in this system, because R receives a number which is negative, Q is no longer involved in the interaction. So the question is, who gets blamed in this case? Fortunately, the answer is the good one, in the sense that Q will be blamed even if it's no longer involved in the session. And in the paper, we have a general result saying that if we have a module P that complies with all the contracts that the module knows about, then no one will be able to blame P, even if other modules conspire against P and try to blame it. Now, in this result, the tricky thing is what it means to know about a contract. And in fact, this notion is a bit difficult to formalize precisely, mainly because, as you've seen in the slides before, during the reduction and during the interaction between processes, contracts are moved around, they are decomposed. We can have stacks of monitors which are turned inside out. Not all the endpoints might have a contract, so reasoning about defining precisely what it means to know a contract is not simple. So in order to prove this result, we actually defined an alternative monitoring semantics, which makes it easier to identify syntactically from the structure of the processes which are the contracts that are known by a particular module P of our system. And by using this, and with these alternative semantics, we can prove the result. And then we show that the two semantics are essentially equivalent, not completely equivalent, in the sense that who identifies a contract violation may be different according to the two semantics, but who gets blamed is uniquely defined. So we have implemented this monitoring system on top of an existing library of binary sessions for OCaml. What I want to show in this picture is the set of dependencies, and in particular these arrows showing you the dependencies between the various parts of the library show you that there are no dependencies going from the lower level to the upper level, which means that all the monitoring machinery can be easily ported to another library. There are no dependencies going from bottom to top. And well, basically this is it. So in summary, we have defined a monitoring system for sessions where the main feature is the fact that the contract of the monitored session may evolve at runtime as the session progresses. And we have been able to do that by essentially reusing all the monitoring machineries that have been defined in previous works without much change, but simply by adding a DSL for specifying contracts for sessions. We have proved the blame correctness results. There are more features that I didn't have time to illustrate during the presentation. In particular, we do support dependent contracts, so contracts where the rest of the conversation may depend on the content of messages that have been exchanged earlier on. We do support contracts for recursive and branching protocols, and these ingredients combined together can be used for specifying quite complex contracts. There are also a number of interesting open issues that may be worth investigated. In particular, we have somehow neglected in this work all the interactions that can arise between functions and sessions. So there are a number of limitations concerning the functions that can be transmitted in sessions. And yeah, we think this could be an interesting directions for future research. So this is basically what I wanted to say. Thank you for your attention, and I'm happy to take questions.